Hello, well, this is Schweitzer. This is a video on oxidation reduction reactions. Now, this video is a little bit longer, so make sure you have enough time set aside. But oxidation reduction, the term oxidation means to lose electrons, and the word reduction means to gain electrons. All right. Now, an atom cannot lose electrons unless there's another atom that's going to be willing to gain them. So whenever we have an oxidizer, something that's oxidizing, you have to have something reducing along with it. The term oxidation and the term reduction originally meant to gain oxygen or to lose oxygen. This definition has now been expanded beyond this to include electrons. You can still use the old definition, but now our current best definition doesn't really match up with the words anymore. So we have these terms called LEO and GER. There's a little bit of an acronym, say LEO, the lion, says GER, lose electrons, oxidize, gain electrons, reduced. I still use these in my head as I'm thinking about oxidation reduction reactions. For gaining and losing electrons, when an atom gains or loses electrons, that means that an atom most likely would be gaining or losing charge. Now this might be quite easy to see, but in some atoms they hide their charge a little better than others, and there's a term called an oxidation state that tracks the charge on an atom and allows you to see if an atom is gaining or losing charge. And more specifically, it might even tell you what specific atom on a molecule is gaining or losing its charge. The definition for oxidation state is the apparent charge on an atom. We will talk more about oxidation states in the chapter of electrochemistry. Today, we're just going to look at the fact that its charge, or oxidation state, is the charge on the molecule. And we'll only be dealing with relatively simple examples of oxidation and reduction. If I want to be able to indicate the charge on an atom, all right, so like I said again, oxidation state is apparent charge on an atom. Gaining electrons, reduction, losing electrons, oxidation. Let's move on to an example. All right, so copper plus silver nitrate. Okay, now in this case, this charge is going to be +1 and -1, and then this is no charge. Over the course of an oxidation reduction reaction, you will see charges changing above. The result of this reaction is going to be Ag by itself, metallic metal, and the copper will be in the reaction like so. All right. Now, for this particular reaction, we have both oxidation and reduction. The copper went from copper no charge to copper +2, nitrate stayed -1. There is a couple ways we could write this reaction, and we'll talk more about it as we go, but there's a method which we would call a molecular equation, and that is the one that currently is listed right here. It's showing ionic compounds together, even though it's not technically together. Now, if I were to write this out as an ionic formula, I would simply separate out the individuals that are ionic and break them apart. So, for this purpose, it would be copper metal, which is all by itself, plus Ag plus ions, plus NO3 -1 ions, all right, yield I'll just put an equal sign there. Ag plus ions. Right, that one's going to be no charge. You can put a little 0 there if you want. Not required. And then the copper will be a 2 plus ion, and the nitrate will be all by itself. There we go. So either way, that is the result of what's called an ionic equation. The net ionic equation is where we will be eliminating some of what's called the spectator ions. And I'll put that right here. A spectator ion is an ion that does not change. Really, it's anything that doesn't change across the reaction. In this case, it's always going to be an ion, or it could be an ion. In this case, the spectator ion would be the nitrate ion. It doesn't change from start to finish. So we remove that, and our net ionic equation would be as follows. Simply the copper metal plus the Ag plus ion equals Ag metal ion plus the copper 2 plus ion. All right, so this is the net ionic equation. Now, from this, we can learn a greater idea of what's actually going on here. And I'm just going to move this down here a little ways so I can, let's put it right here. Okay, so when we're dealing with oxidation and reduction reactions, we have one thing that's being oxidized, one thing that's being reduced. Which one is it? So in this case, the copper is going from Cu with no charge, I'll just do this, to coppers, which is Cu2 plus. And then the silver Ag is going from A plus to an Ag with no charge. The question here is which one is being oxidized and which one is being reduced. You can see that this is a before picture and this is an after picture. So before it's neutral, meaning copper has the same number of protons and electrons, and for copper, not that it really matters at this point, but copper normally has 29 electrons and 29 protons. Now has 29 protons and only 27 electrons, hence a positive 2 charge. So these two sides have to be equal, hence the equal sign or the arrow. So at this point, I would put down in this thing that this guy right here also has now lost 2 electrons. Okay. I'm going to back this up here. There we go. All right. And before picture, after picture, this guy has 1 less electron than here, so both sides have to be equal. I'll go 1 electron. There you go. So 1 electron, positive 1, negative 1 equals this side. No electron here, 0, 2 plus negative 2 equals, both sides are equal. So this is really what's happening here. Rather than the nitrate being part of the reaction, really the copper metal is losing 2 electrons, here they are, to form this guy. The silver ion picks up these 2 electrons to form this guy right here. Okay. You also should be apparent that every time the copper atom loses 2 electrons, 2 silvers are able to complete this process because it only requires 1 electron. So this guy can run twice every time. This guy can run twice after this one runs once. All right. So whenever we're balancing these things, I want to make sure my electrons here and here are equal. This whole process goes twice. Electrons lost are electrons gained. Runs once, this one loops twice. runs once, this one loops twice. Overall reaction at this point, balanced reaction, would be right here. I would have my copper with my no charge plus 2 Ag pluses yields copper 2 plus 2 Ag with no charge. Okay. Now again, if you aren't looking at the electrons, you might think that was balanced before, but the electrons were not being accounted for, and we were 1 electron short here, so this one has to run twice. And this is the balanced chemical reaction. Okay. There's one more thing that we do with this, is to ask ourselves the question, I'm just going to get rid of this right here, and that is going to be, does this reaction actually run? And this might get rid of that. Nope. Let's do this. There we go. All right, so does this reaction actually run? That's an important question to ask, and just because we do something on paper means that, okay, this guy is essentially giving this guy an electron, and then he gave another one an electron. There is an exchange of electrons taking place here, but just because it happens on paper doesn't mean it actually happens in real life. So we have to have some way to measure. This is an exchange of 2 electrons. So there's kind of a dynamic here where we have one individual, okay, is X, let's just say individual Y. This guy has the electron. He wants to give this guy the electron. There's kind of a dynamic here where, okay, how much does X want to get rid of the electron? How much does Y want to take the electron? This is a full dynamic here. Sometimes I make the analogy between, your grandma's house and she's making you eat food. And even though you're full, you still say yes. You don't want the food, but okay, grandma's pushing food on me, so I take the food. Same analogy here. Does X want to get rid of the electron? Does Y want to take it? Maybe X really wants to get rid of that electron, but Y doesn't want it, but it's being forced to take it. Or maybe X really doesn't want to get rid of the electron, but Y wants it badly, so it takes it. Or maybe a situation where X really wants to get rid of the electron, Y really wants to take it, so it's a great benefits both sides. That being said, everything has an ability to accept or get rid of electrons, which we call an electropotential. Okay, and there's a lot of information here. I'm going to eventually go through a couple examples to show you how this works. Now, an electropotential is a substance's ability to pick up or take electrons. It's a relative scale, and it is based off of the pickup or drop of hydrogen grabbing an electron. So in this case, you go to Science Resources, and you'll see reduction potentials chart, and this is right here. Okay, pretty standard chart here. Okay, again, it's based off hydrogen, so hydrogen is 0. Everything else is relative to that. All right, so how do we use this chart? This is going to tell us the relative abilities of something to be able to pick up or take electrons. So you find these charts. Now this chart is only reductions, mind you. So this, and I should clarify again, that because this guy here is losing electrons, this is going to be oxidation. Anytime the electrons are on the product side, this is oxidation. Anytime they're on the reactant side, it is reduction. Okay, oxidation, reduction. Because this is a reduction, you're only going to find reductions on this chart. Let's go find the value. Again, this tells me how much a particular substance wants to pick up electrons. Now, a substance that doesn't want the electrons, this value will be negative. If it's happy, then take electrons, it would be positive. This means it doesn't want to, this means it wants to. All right, so negative means no. All right, so again, let's go to this chart here. Might be right here. There you go. So let's find the, which one is it? Is the silver plus ion. Okay, so grab it there. And right here is this value. Okay. It's positive 0.8. So this means, does silver plus ion want to pick up an electron? Yes. It's positive value. It does. Okay, so let's go back here, and I'm going to write down right here positive 0.8 volts. Okay, and it's measured in volts. All right, let's find this. Now, we won't find this exact one on the chart because this is oxidation. We'll find the reverse of it, which is reduction. Okay, go here, grab this guy, and it is right here. Right there. Okay, now this is the reverse of the reaction, which is a positive 3,4 volts. I want the reverse of this one, so I flip the sign. That's important. Flipping the sign flips the reaction. So all the reductions around here, if you want to find an oxidation version, you just take it and you flip it. So this one, rather than being a positive 0.3 volts, is a negative 0.34 volts. Add them up for my total voltage. And this guy does not want to take the electrons, but the silver wants to get rid of them. I shouldn't say that this guy doesn't want to get rid of its electrons. The silver doesn't, but the silver wants to take them more than this guy does not want to get rid of them. So my ending point here is a positive 0.46 volts. A lot of information here. Because it's positive means it's going to run. Okay. Does this reaction actually run with a positive voltage? The answer is yes. Now, even though I doubled this and runs twice, I don't double my voltage. It just runs 1 to 1. Okay. Let's try another example here. I got a couple here. I'll just get rid of this. Okay. All right, so let's try another example of this. Let's try NaF plus, let's go with chlorine as my guy here, plus chlorine, okay. And I'll just use an equal sign here. And the result will be NaCl plus F2. Okay. Now, in this particular example, and there's lots of stuff here, I give you the product, but eventually we should be able to come up with them on our own. Now, the charges on these things. This thing is going to be a +1, -1, no charge element. +1, -1, no charge element. This tells me that this is an oxidation reduction reaction, or commonly known as a redox. Okay. Now, split this thing into half reactions. We want to know, is this reaction going to run or is it not going to run? All right, so Na plus doesn't change on your side. Now keep in mind these are aqueous ionic compounds. So these would be dissolved in water, and this would be a pure substance and a pure substance. We're mixing them. Na plus F negative plus chlorine gas yields Na plus Cl negative plus fluorine gas. It seems complicated at first, but if you do a couple examples, you'll see they're very similar. In this case, the sodium does not change, so this is the spectator ion. The F negative plus chlorine gas yields chloride ion plus fluorine gas. Okay, just to make sure they're balanced on both sides, I'll have 2 of these guys and 2 of those guys. All right, so split into the half reactions. The 2 fluoride ions go to F2, and the chlorine goes to 2 Cl negatives. Who is being oxidized, who is being reduced? So they got to be equal on both sides. I have two negatives here, so I have no charge here. So I need to add 2 electrons to this side. This means that these two are now equal. And 2 negative would be plus 2 electrons on this side. Again, they are now balanced. This guy is losing electrons, so this is called oxidation. This guy is gaining electrons, this is called reduction. The fluoride is hence going to give the electrons to the chlorine. Therefore, the chlorine becomes chloride, and the fluorine returns to fluorine. Fluoride returns to fluorine. It is a 1-to-1 ratio, so my balanced reaction would be 2F negative plus Cl2 yields F2 plus 2Cl negative. All right, so the question is, does this reaction actually run? I have a reduction reaction I can find right on my chart, and there it is. Look for the reduction of fluorine as the top one. Fluorine to fluoride. I do believe that's what we want. Let's check and make sure. Ah, this is reversed. I have fluoride to fluorine. Okay, that's not right. So rather than being a positive 2.87, yeah, this is oxidation. So I should not find it on the chart. It should be the reverse of the chart. Rather than being a positive 2.87, it's going to be a negative 2.87. This guy absolutely does not want to take an electron. It will need to be forced. All right, let's go find the reduction potential for chlorine. Here you go. And chlorine is a little lower, and it is 1.36. So this will be a positive 1.36. In the end, my value is going to be negative. I can subtract these two values. This would be a 1, this would be a 5, this would be a, looks like a 1, and 1.51 volts negative. This means it is not going to run. Now, could we get this to work? Yes, but we'd have to literally pump energy into it to drive this reaction. It will not happen on its own. If this were a battery, and sometimes batteries do work off these principles, this battery would need to be driven to run this direction. Would not happen on its own. Two examples, one where one runs, one where one doesn't. Okay, let's look at an example where we would have to predict what happens in a chemical reaction. And this starts to get a little more complicated, and you have to have a greater understanding of what's going on in the chemical reaction. So let's try an example of, let's say, zinc. All right, zinc. Okay, plus metal. Let's go plus copper nitrate. All right. Okay. Now, I want to, at this point, predict what my products are going to be. Okay, so let's put that up top. I'm going to try to predict my products, or my potential products. All right, now, in this case, my zinc has no charge. Okay, my copper is a +2. My nitrogen's a -1. This guy, zinc, has the ability, only it's a metal, the zinc can become no charge, or it can go to zinc 2+. It can give away electrons. There is only one option of someone to take these electrons. The nitrate isn't going to pick up more electrons. That's its only standard state. So you have to kind of rely on what you know about the ions available. Copper, on the other hand, Cu, could be copper +2, which it currently is. It could be copper +1, or it could be copper, plain old copper metal. So technically, if the zinc were to dump electrons onto the copper 2+ ion, it could drop it to copper +1, or even all the way down to copper no charge. That is a potential possibility. It could not dump something on there that already is negative. Okay, so my options here is the zinc no charge, plus copper 2 plus NO3 2 minus 1. My option would be for the metals exchanging with metals. And that's kind of a pretty common idea here, is that metals exchange with metals and non-metals exchange with non-metals. And this is just one example. You would need to be able to practice this to get proficient at it and to really feel like you understand what you're doing. So in this case, the zinc would become zinc. I'm going to eliminate this altogether. I'm just going to go with this. Remove the nitrate from the problem. It is just simply going to be a spectator ion. The zinc will give the copper its electrons, and let's just say that it pushes it all the way to zinc 2 plus and copper no charge. Okay. At this case, the overall reaction will look like this: zinc metal plus copper nitrate goes to zinc nitrate plus copper metal. Again, it's balanced. This guy lost 2 electrons, this guy gained 2 electrons. It's a 1-to-1 ratio, so this is all balanced. We'll stop there. The video's gone long enough. Again, this is complicated stuff, quite a bit of chunk of stuff to try and grasp all at once, but with time practice, it will become quite easy.